For most of human history, the stars felt like a mythic backdrop, a painting on the ceiling of the night. Now we like to tell ourselves that we live in a space age. We have seen photos from Mars, we have watched rockets land upright, and we casually talk about becoming a multi-planet species. It sounds bold and confident, as if interstellar travel is just the next software update. But the harsh reality is that we are not even close to being a true spacefaring civilization. We are struggling with the training wheels, because if we look honestly at what it takes to send a small group of fragile humans to our own neighbouring planet and bring them back alive, the story turns from triumphant to terrifying. And that is where the real test begins. If you strip away the romance, a crewed mission to Mars is a story about locking several people inside a metal can, smaller than many apartments, and then throwing that can into deep space for most of a year, with no possibility of rescue. Imagine the cabin. Every sound is recycled air hissing through vents, pumps pushing water, fans humming around the clock. Outside the thin wall there is vacuum, hard radiation, and a temperature swing between deep cold and unfiltered sunlight. The distance to the nearest emergency room is tens of millions of kilometers. When something breaks, there is no warehouse, no spare parts desk, only what you brought and what you can improvise. On Earth, if a system fails, someone can drive over with replacement parts. In low orbit, a supply spacecraft can dock within days. That safety net is what makes the International Space Station survivable. Mars does not offer that kindness. The orbital mechanics that make a trip efficient are the same mechanics that turn it into a trap. The shortest energy path to Mars is a gentle spiral called a transfer orbit. You wait for the planets to line up in just the right way, then you fire your engines at exactly the right time, and you fall along a long looping path that intersects Mars months later. Once you commit to that path, there is no quick U-turn. The energy needed to slam on the brakes and reverse course is far beyond what any realistic mission can carry. If something serious goes wrong halfway, you do not simply swing the nose around and head home. You are on a rail written by gravity, sliding forward whether you like it or not. It is like stepping onto a train line where the next station is on another world and the doors are welded shut until you arrive. We tell this story as adventure, but if you were one of the people in that cabin, how would it feel after the first few weeks, when the novelty has worn off and the math of no return has really sunk in? Now layer on the problem of everything your body needs to stay alive. Air is not a given. Water is not a given. Food is not a given. A Mars ship is a floating ecosystem that tries to do what our planet does for us for free. Carbon dioxide scrubbers must pull your waste gas out of the air. Filters and membranes must reclaim water from sweat, breath, and urine until the same molecules have passed through everyone many times. Machines must keep the pressure inside just right so that your blood does not boil and your lungs do not collapse. Every one of those systems is built with backups and safety margins. Yet we know from long experience that devices fail in ways designers never expected. On the surface, we reassure ourselves with phrases like triple redundancy and fault tolerance, but stacking 3 copies of the same design does not protect you from flaws that they all share. A subtle manufacturing defect, a piece of software that misbehaves only in a rare sequence, or a tiny leak that slowly eats away at a joint can defeat an entire layered design. The longer you stay out, the more chances the universe has to exploit every overlooked weakness. When missions last weeks, those odds can be acceptable. When missions last years, the risk climbs quietly in the background like interest on a debt. And this is all before we talk about the human mind. On Earth, if a job becomes unbearable, you can quit, walk away, or at least open a window and breathe outside air. In a ship between planets, there are no doors that lead anywhere else. You wake up every morning with the same handful of faces, the same narrow corridors, the same monotone hum of machinery. The view out of the small window, when you are allowed to look, is a slowly shifting starfield that does not care if you are happy or not. We have simulated pieces of this experience in isolation studies. Crews have lived for months inside sealed habitats on mountainsides or in polar regions to mimic confinement and isolation. They had artificial delays added to their communication with the outside world to reflect the time light needs to cross interplanetary distances. Even with the knowledge that they were still on Earth and could walk out in a true emergency, people reported tension, irritability, conflicts over small things, and a creeping sense of unreality. The mind starts to push back when it realizes that its environment is both completely safe in the moment and completely inescapable in the long run. Now imagine doing all of that with a communication delay that slowly stretches from a few minutes to close to half an hour each way as the planets drift farther apart. In a crisis, you cannot call home and get real-time advice. At best, you send a message, wait, and receive an answer almost an hour after you ask the question. In practice, this means that every emergency, from a medical issue to a technical failure, must be handled by the crew alone. Mission control becomes less a live guide and more a distant archive of suggestions. These psychological pressures are not side details, they can directly threaten the mission. A crew that does not trust one another, or that begins to doubt the purpose of their journey, is a crew that will cut corners, ignore checklists, and make impulsive decisions. Even a small drop in discipline can compound into real danger when your environment is as unforgiving as deep space. And we have to remember that the people we send to Mars would not be average. They would be screened and trained far beyond normal levels. If even they struggle, what does that say about the rest of us and our dreams of populating the galaxy? So far, we have talked about isolation, confinement, and the fragile string of technologies keeping a crew alive. All of that is challenging, but at least it sits within the familiar territory of human behavior and mechanical engineering. There is another enemy, though, that does not care about our procedures or our group therapy sessions. It is invisible, almost undetectable to our senses, and it fills the space between planets. When we step beyond Earth's magnetic shield, we step into an ocean of high-energy particles. Here on the ground, we are protected by a combination of our thick atmosphere and the giant bar magnet at our planet's core. Charged particles from the Sun are deflected away or slammed into upper air, where they create harmless light shows that we admire as auroras. Cosmic rays from far away are largely blocked or slowed before they reach the surface in force. We live at the bottom of a protective well of air and magnetism, so complete that it took us a long time to even discover that this invisible rain existed. A spaceship on the way to Mars lives at the top of that well, not the bottom. There is no thick air above it. There is no strong magnetic field wrapped around it. When energetic protons from a solar flare wash over the region, they see a thin skin of metal and a few centimeters of water or plastic, and then they see your cells. When heavier atomic nuclei from a distant supernova arrive, they punch through even more easily. They are so fast that each one carries the energy of a small bullet compressed into an object smaller than an atom. One of the sobering moments in our real history of Mars exploration came from a robot, not a person. During its cruise to Mars, the Curiosity rover carried a radiation instrument inside the spacecraft that recorded the dose it received along the way. When scientists translated those measurements into the dose a human would absorb in the same environment, the numbers were not reassuring. For a round-trip mission with a stay on the surface, the accumulated exposure would be comparable to hundreds of medical chest X-ray images, concentrated into a few years of life. That pushes right up against career limits used to protect astronauts from an increased lifetime risk of cancer. We should be clear about what this means. The problem is not that a human would drop dead halfway from acute radiation sickness. It is that each particle track that slices through tissue can clip DNA strands, disrupt neural circuits, and set off long-term changes that might not show up until years after the crew has returned. It is like filling an already risky adventure with lottery tickets for later cancers and cognitive decline. And that is with the relatively modest energies involved in a Mars journey. Between stars, the exposure would be even harsher and longer. Engineers have tried to design their way out of this by adding shielding. The instinct is simple. If something is dangerous, put more material between you and it. For low-energy radiation, this works. A few centimeters of aluminium or plastic can make a big difference against certain solar particles. But the highest energy cosmic rays do not politely stop. They smash into the shielding itself and create showers of secondary particles. Instead of one heavy nucleus sliding through your body, you can get a spray of lighter fragments and gamma rays. In some scenarios, adding more metal around a crew can actually make parts of the radiation environment worse rather than better. So people have turned to lighter elements, especially hydrogen-rich materials like water or polyethylene. These do better at absorbing and slowing heavy charged particles without so many dangerous byproducts. The catch is simple and brutal. You need a lot of it. To reduce the radiation dose to levels that would be considered comfortable for a multi-year mission, you would have to wrap the living quarters in several meters of shielding. That adds mass. Added mass demands more fuel. More fuel demands bigger engines and more structure. The ship gets heavier, which makes every other problem harder. This is one of the central patterns that repeats whenever we push on interstellar dreams. The more honestly we confront one obstacle, the more we are forced to add complexity in mass to solve it, and the more the rocket equation punishes us. If we make the cabin bigger to ease psychological strain, we need more life support and more structure. If we add redundancy, we add weight and more parts that can fail. If we add radiation shielding, we add huge amounts of mass that must be accelerated and decelerated. Each fix pulls the ship away from elegant concept art and toward a sprawling, fragile, expensive compromise. At this point, it is worth asking a quiet but uncomfortable question. We talk often about sending colonists to Mars and then one day journeying to nearby stars. Yet we have not even flown a single human being beyond low Earth orbit since the early 1970s. The orbital outpost that we celebrate as a symbol of our space age drifts a few hundred kilometers above the ground, moving fast but held tight by gravity. Our heroic future is being projected from a position that is still, in cosmic terms, barely off the surface. When you step back and see the full picture, Mars becomes more than a destination, it becomes a mirror. It shows us what happens when bold rhetoric meets the physics of space and the limits of biology and psychology. Just reaching that small red dot in a sustainable way would demand an evolution in our technology, our institutions, and our willingness to accept real risk. And yet, compared to the gulf between stars, Mars is almost touching our fingertips. So the question we are left with is not just whether we can build a ship that survives the trip to our neighbour, but what the struggle to do even that tells us about our chances of ever crossing the far wider ocean beyond. To answer that, we have to step past Mars entirely and confront the true shape of the radiation storm and the energy wall that wait in the dark between the stars. When you hear the phrase radiation storm, it is easy to imagine a weather event that comes and goes, a spike that you can ride out and then forget. The space between planets is not like that. Out there, radiation is not a passing storm, it is the climate. It is the permanent background a ship has to live in. And once we move beyond Mars and start thinking about decade-long interstellar journeys, that climate turns from an engineering problem into something closer to a physical and neurological wall. We can divide this invisible danger into two broad families. One group comes from our own star, the other comes from everywhere else. Solar particles are the familiar troublemakers. Bursts from eruptions on the Sun spray high-energy protons and electrons through the inner solar system. They can spike suddenly, last for hours or days, and then fade. Galactic cosmic rays, on the other hand, are the ancient, patient enemy. They are atomic nuclei from distant supernovas and other violent events, stripped of their electrons and driven to speeds close to that of light. They cross the galaxy for millions of years and do not care at all about our schedules. Solar storms are dangerous, but at least they have patterns. We can monitor the Sun, predict active cycles, and sometimes give astronauts warning that a flare is coming. In principle, you can design a ship with a storm shelter, a den in the middle where water tanks and supplies form a thick protective cocoon. When a warning arrives, the crew huddles there until the burst passes. It is not comfortable, but it is at least a threat you can duck. Cosmic rays do not give you that luxury. They do not arrive in neat bursts you can hide from. They are a constant drizzle of bullets made of matter itself, each one blazing fast enough that, in the vacuum of space, it might travel across our entire solar system in less time than it takes you to eat a meal. They never turn off. They do not weaken when you cross some boundary. and even at their low flux, over years and years, they add up. To understand why they are so hard to block, it helps to zoom in to the level of a single particle track. Picture a heavy nucleus, maybe iron, racing through space. It is not big in any everyday sense. It is far smaller than an atom. Yet because of its speed, it carries staggering energy in that tiny package. When it hits the hull of a spacecraft, it does not politely stick. It slams into the metal lattice, tears atomic nuclei apart, and triggers a spray of secondary fragments, each with its own path. If the primary particle or its fragments pass through a human body, they leave a trail of ionization behind them. Along that trail, electrons are ripped from molecules, chemical bonds are broken, long strands of DNA are cut or cross-linked. Sometimes the cell can repair the damage. Sometimes it misrepairs it and quietly lays the seed for a cancerous mutation. Sometimes it simply dies. Multiply that by the length of an interplanetary or interstellar mission, and you start to see why space agencies take the risks so seriously. Medical radiation therapy on Earth uses similar physics, but in a controlled, targeted way. Doctors aim beams at tumours and carefully limit the dose to healthy tissue. In deep space, there is no control and no targeting. The entire body, including the brain, is slowly painted with random tracks. The dose at any moment is low, which is why crew members on the International Space Station do not drop from acute sickness. But a journey to Mars, and even more so a journey between stars, means living in that bath with no thick atmosphere above and no magnetic shield around. The first instinct, as with Mars, is to add shielding. Stack more material between the crew and the outside. For certain types of radiation, especially lower energy charged particles, this works well. A few centimeters of aluminium, water, or plastic can knock down the intensity and protect soft tissue. The problem is that cosmic rays carry so much energy that they can turn your protective wall into a secondary source of radiation. When a heavy cosmic ray nucleus collides with a thick metal shield, it can shatter into many lighter fragments. These fragments often include protons, neutrons, and lighter nuclei that spray into the cabin from the inner face of the wall. Some of them are more biologically damaging per unit of energy than the original particle, so you end up in a strange situation. A modest amount of shielding reduces the total dose a bit, but beyond a certain thickness, adding more metal can actually increase the effective biological damage inside. This is why researchers have looked closely at hydrogen-rich materials. Hydrogen is light, just one proton and one electron. When a heavy nucleus hits a hydrogen-rich material like water or polyethylene, it tends to lose energy in smaller steps instead of breaking into a big shower of fragments. The overall pattern of secondary radiation is easier to manage. In principle, you could build the walls of the crew area from tanks of water or from layers of plastic panels. Yet the numbers are relentless. To cut the radiation dose to something like what you would experience on Earth over the same period, you do not need a thin film. You need meters of shielding around the crew in every direction. Imagine trying to wrap a habitat module in a glob of water 3 meters thick, or in plastic bricks that amount to hundreds of tons of extra mass. Then remember that every kilogram must be pushed up out of Earth's gravity well and then accelerated for the journey. The rocket equation does not care about your good intentions. It simply states that for a given type of engine and exhaust speed, every extra kilogram of payload demands a rapidly growing amount of propellant. If you double the dry mass of the ship with thick shielding, you do not just double the fuel, you might multiply it by many times, until the launch vehicle becomes absurdly large. We will explore that equation more deeply later, but you can already feel how radiation and propulsion are tangled together. Even if we accept higher risk of cancer, we still have to confront a more subtle danger. Ionizing radiation affects not only the body, but also the brain. Studies on animals exposed to simulated cosmic ray fields in accelerators have shown worrisome changes in cognition, memory, and mood. The doses are often higher than a human would experience on a Mars mission, and translating from mice to people is complicated. Still, the hints are clear enough to be unsettling. Imagine a crew who left Earth fully trained, mentally sharp, and emotionally stable. Years into a voyage, after living under constant low-level particle bombardment, what if their ability to concentrate slips by just a small amount? What if their reaction times lengthen? What if their mood tilts toward anxiety or depression? In everyday life, those changes would be serious but manageable. Inside a closed system, where every decision interacts with life support and navigation, a slight cognitive fog could be catastrophic. There is also the question of reproductive health. Long missions probably demand some plan for children, whether for a true generation ship or simply as insurance against tragedy. Radiation does not treat eggs, sperm, or developing embryos kindly. Damage to germ cells can quietly propagate into the next generation, causing birth defects or subtle issues that only become obvious later. Protecting a growing child from cosmic rays in deep space would require even stricter shielding than protecting an adult. All of this pushes us toward exotic ideas. People have proposed creating artificial magnetic fields around ships, using superconducting coils to mimic Earth's magnetosphere on a smaller scale. In principle, charged particles would be deflected around the habitation area. It is a beautiful idea, turning physics itself into a shield. In practice, the technical demands are staggering. You need coils large enough and strong enough to bend the path of extremely energetic ions, powered for years without failure, with structures that can withstand the forces generated by their own fields. There are also biological countermeasures. Could we tweak human DNA to be more resistant to radiation, boosting repair pathways, or borrowing traits from hardy organisms that survive intense exposure, like certain bacteria or tiny animals? Could we flood the body with drugs that mop up free radicals before they trigger cascading damage? Research on radioprotective agents and gene editing is real and ongoing, but every new layer of complexity increases the room for unknown side effects. A crew genetically engineered to survive cosmic rays might pay a price somewhere else in their biology. At this point, you might feel a rising sense of impossibility, as if the universe has set up a trap to keep biological life penned near its home worlds. But we should be careful not to slide into fatalism. The radiation wall is real, yet it is also a clue. It tells us that interstellar travel will not be achieved by simply scaling up the rockets and habitats we use for short missions. It will require a shift in how we think about risk, time, and even what it means to be human. We can also flip our perspective. Instead of only asking how we protect human bodies from space, we can ask how we redesign missions so that fewer human bodies are exposed for less time. The rising power of robotics, artificial intelligence, and miniaturized instruments already lets us send probes that do more with less mass than entire fleets of earlier missions. The twin Voyager spacecraft, old and far away, still talk to us with transmitters that would look laughably weak by modern standards, and yet they continue to send data from beyond the planets. If tiny machines can travel for decades and still function, then one path forward is obvious. Use machines wherever we can, and keep human presence for moments and places where perception, judgment, and experience add something irreplaceable. That does not satisfy our desire to plant boots everywhere, but it might be the only way to push our senses, and our knowledge, out into the more distant parts of the universe. The radiation that would quietly shred a human nervous system over years is much less of a problem for solid-state electronics designed with redundancy and shielding in mind. Still, even robotic craft must obey the same physics of motion. Whether we send people or machines, the interstellar medium is not only a sea of radiation, it is also a vast, nearly frictionless desert where speed is both necessary and dangerous. The faster we go, the shorter our exposure to cosmic rays. But the faster we go, the more we invite new threats, from micrometeoroid impacts to the brutal energy demands of acceleration and braking. So we end up at a sharp crossroads. If we crawl between the stars at gentle fractions of light speed, radiation doses and mission durations stretch into centuries and millennia. If we try to sprint, we slam into the unforgiving mathematics of the rocket equation and the strange effects of relativity. To see just how tight this trap is, we need to leave radiation behind for a moment and turn directly to the problem of speed itself, and to the deep energy chasm that opens up when you try to make a starship truly fast.
Imagine a ship that wants to go just a little faster than our fastest probes. Nothing dramatic, nothing close to the speed of light. You might expect the fuel needs to rise in a gentle, manageable way. Instead, the numbers explode.
Every extra bit of speed costs more fuel, which adds more mass, which then needs even more fuel to move. It is a spiral, and it is captured in one quiet equation that has haunted rocket designers since the middle of the last century. The core idea of that equation is almost painfully simple. A rocket moves forward by throwing stuff backward. To go faster, you must either throw the exhaust out at higher speed or throw more of it. But the propellant you throw backwards starts the journey as cargo, sitting in your tanks and making the rocket heavier. Early in the burn, when the tanks are full, much of the thrust is spent accelerating fuel that you are just going to throw away later. At low speeds, this is annoying but not fatal. At interstellar speeds, it becomes a wall. Chemical rockets, the kind we use now, hit this wall very quickly. They push exhaust out the back at a few kilometers per second. That is enough to reach orbit and to nudge a spacecraft onto a path to Mars or Jupiter. But if you want to send a large ship to a significant fraction of the speed of light, the math becomes absurd. The rocket would be mostly fuel, with a tiny pocket in the middle for the crew. Add life support, shielding, and a sturdy structure, and the required propellant mass climbs into ranges that no realistic launch system can handle. Even within our own solar system, we have had to play clever games to get decent speeds. The fastest human-made object so far is not a starship, but a solar probe. It uses repeated gravity assists, looping past planets and skimming dangerously close to the Sun, trading orbital energy and heat for speed. This trick lets it reach hundreds of thousands of kilometers per hour relative to the Sun, a number that sounds thrilling when you first hear it. In everyday terms, it is astonishing. In interstellar terms, it is painfully slow. At that record speed, you would need tens of thousands of years to cross the gap to the nearest star. The problem is not that we cannot move fast compared to our daily lives. The problem is that the universe is big enough that even impressive velocities shrink to a crawl. So we start to dream about something bolder, and we turn our eyes to the ultimate ceiling for speed in the universe, the speed of light. According to relativity, nothing with mass can reach the speed of light, but you can get arbitrarily close. The closer you get, the more strange things become. From the perspective of an outside observer, your clocks tick slowly, your rulers along the direction of motion shrink, and your mass effectively behaves as if it is increasing. From your own perspective on the ship, however, you experience something very different and tempting. Time dilation starts to work in your favor. If you could accelerate long enough and close enough to the speed of light, you could, in principle, cross enormous distances within a single human lifetime as you experience it. Decades might pass for you, while centuries or millennia pass back home. This is the famous idea of the relativistic journey. The universe outside races by in fast motion. The light from stars is shifted and distorted, and you arrive far away, without having to endure thousands of years of subjective time. On paper, that sounds like the perfect workaround. You do not need immortal humans or frozen ones. You just need to build a ship that can accelerate constantly at a comfortable fraction of gravity, turn around halfway, and decelerate the rest of the way. The passengers enjoy artificial gravity from acceleration and experience a manageable stretch of time. The price is paid in energy, not in human years, and that price is vast. Kinetic energy grows with the square of speed. When you are driving a car, this is an annoyance that makes high-speed crashes more dangerous. When you are trying to push a multi-ton spacecraft to a significant fraction of the speed of light, that square term becomes monstrous. Double the speed and you quadruple the energy. Push to 10 times the speed and you need 100 times the energy. By the time you are approaching 9/10 or 99 hundredths of light speed, the required energy rivals the total power output of entire civilizations. We can try to make this more concrete. Suppose you have a ship with a mass comparable to a large modern airliner, a few hundred tons including structure, shielding, and payload. To push that mass to a fraction of light speed, even before you worry about deceleration at the far end, You need energy on the order of what our entire species produces in months or years. And that is if you had some perfect, lossless engine that converts stored fuel to motion with near total efficiency. Real engines always waste energy as heat and radiation. They leak. So we look for ways to cheat the rocket equation. One idea is to move the energy source off the ship. Instead of carrying all the fuel with you, you let some remote system push you. For example, a giant laser array on or near Earth could fire at a sail attached to the spacecraft. The light carries momentum. The sail reflects it and gets pushed forward. Suddenly, you do not need propellant tanks that dwarf cities. You just need a light, reflective sail and a powerful beam behind you. This is the concept behind laser sail proposals. For tiny probes weighing grams or kilograms, the idea is almost within reach. For a crewed starship with habitats and shielding, the requirements seem mythical. You would need an array of lasers spanning kilometers, powered by a significant fraction of the global electrical grid, running steadily and with high precision for long periods. The beam would have to stay locked on a moving target millions of kilometers away, adjusting for diffraction and interstellar dust. Any interruption would bleed away momentum and complicate navigation. Even if you solve those aiming problems, you hit another wall. A laser sail mission that accelerates continuously has no easy way to slow down at the destination. The same beam that pushed you from home cannot reach you from behind once you are halfway to another star. You arrive in the new system going very fast and essentially perform a furious flyby, snapping a quick look before you vanish into the dark again. For light probes, that might be acceptable. For human crews, it would be an almost cruel outcome. A one-time glance at a new sun and then endless, deep space. There are proposals to use magnetic sails or plasma interactions with the local interstellar medium to brake, but these are speculative and rely on subtle forces spread over long distances and times. The more realistic picture, at least for the near future, is that interstellar travel at high fractions of light speed might be possible for small, uncrewed payloads, long before it is remotely plausible for habitats full of humans and their fragile ecosystems. On top of the raw energy cost, there is another problem that grows with speed. Space is not completely empty. It is filled with dust grains and thin gases. At ordinary spaceflight speeds, these are minor hazards. At relativistic speeds, even a tiny dust grain becomes a high-energy projectile. When you slam into a micrometeoroid at a significant fraction of light speed, the collision releases energy comparable to an explosive. The grain and part of your hull can vaporize. The shock can ripple through the structure. To survive that regime, a ship would need a forward shield that is constantly absorbing and deflecting impacts from dust and gas. One idea is to let a cloud of plasma or loose particles ride ahead of the main body, sweeping up the worst of the debris. Another is to accept erosion and overbuild the nose with enormous sacrificial layers. Both approaches add mass, complexity, and power demands, and the faster you go, the worse the problem becomes. Relativity starts to help with time, but it punishes you with energy and impact risk. You might be wondering if there is some threshold where all of this suddenly gets easier, some magic speed or engine type that flips the script. For the laws of physics as we currently understand them, there is not. Every conventional proposal, from fusion rockets to antimatter drives, must still confront the square law of energy and the rocket equation. Fusion could, in principle, provide much better exhaust speeds than chemistry, and antimatter could unlock even higher energy density. Yet both come with staggering technical and safety challenges. Fusion has eluded us for practical power generation even on Earth, where we can build huge, delicate machines, shut them down for repairs, and surround them with thick shielding. Doing fusion in a compact, reliable and controllable way inside a starship for decades would be a leap beyond anything we can currently demonstrate. Antimatter promises maximum energy per unit mass, but we can barely produce atoms of it in laboratories, and storing significant amounts safely would be like carrying a city-destroying bomb that must never touch the walls. Relativity does give you one curious gift. As your ship goes faster and your perspective diverges from that of observers back home, the effective energy cost per unit of your onboard time can feel less dire. Accelerating steadily at a comfortable acceleration for a long enough period, you can cover tremendous distances in what feels like a manageable span of years for the crew. The outside universe will see your energy use and speed as enormous, but your clocks and your bodies only experience the local acceleration and onboard time. This is a captivating thought experiment. It suggests that a sufficiently advanced civilization with access to enormous energy sources and extremely reliable propulsion might send crews on journeys where they sleep in their bunks, grow old, and die after visiting distant regions of the galaxy, while countless generations pass on their homeworld in the meantime. From the crew point of view, the galaxy becomes travel-sized. From the home point of view, those missions become almost like one-way trips to a far future. For us, right now, this is not a practical flight plan. It is a way of understanding the shape of the barrier. We do not lack clever ideas. We lack the ability to harness and control energy at the scale that relativistic travel demands. And we lack materials and systems robust enough to survive high-speed impacts and long-term operation without maintenance. That gap is not a matter of better funding next year. It is the difference between a young technological species and one that has restructured entire planetary energy systems for millennia. There is another twist. Even if we someday build engines that can push ships to high fractions of light speed, the universe itself will not wait politely for us. Stars move, galaxies drift. Over cosmic timescales, the fabric of space expands. The targets we might aim for today will not be in the same places when some distant ship arrives, many centuries or longer in the future. Navigation becomes a problem not just of precise aiming, but of predicting the long dance of stars, tides, and dark energy. All of these layers together form the speed trap. At low velocities, space travel is slow, but just about manageable. As you push higher, each new increment costs more energy, more shielding, more precision, more risk. Beyond a certain range, the requirements push into a realm where entire planets would have to be devoted to building and powering a single mission. And even then, the crew would be betting their lives on machines that must perform flawlessly across distances and timescales that we have never tested. So far, we have been talking in generalities. To see how this all plays out in a concrete case, it helps to pick an actual destination, not just a vague idea of another star. There is one in particular that we always come back to, a small red neighbour whose name has become almost a synonym for interstellar hope, and whose apparent closeness hides just how far away the rest of the universe really is. That neighbour is Proxima Centauri, a dim red dwarf clinging to the edges of the triple star system we casually call Alpha Centauri. On the sky it is invisible to the naked eye, yet it has become a kind of celebrity in science headlines and science fiction. It is the closest star beyond the Sun, a little more than 4 light-years away. In a universe measured in tens of thousands of light-years across for a single galaxy, that distance feels almost intimate. We look at it and think, this is the first real step, the shallow end of the interstellar pool. If we can reach Proxima, then surely the rest will follow. The excitement surged when astronomers found a planet there, Proxima Centauri b, orbiting in the temperate zone where liquid water on a surface might be possible. The reality is complicated by flares, stellar winds, and orbital details, but for the public imagination, none of that mattered. Overnight, there was a rocky world around the nearest star that might be at least somewhat Earth-like. Articles bloomed with talk of second Earths and nearby homes. The distance of just over 4 light-years was repeated so often that it began to sound more like a commute than the gulf that it truly is. Out of that mood came a seductive idea. Maybe, with the right propulsion, we could send a crew there in something like a human lifetime. You see the number 4? You imagine a travel time of a few decades, and a phrase appears that sounds comforting. A 40-year mission. Long, difficult, but still within the span of a single generation. Long enough that the people who launched the ship might live to see their names in messages from another sun. It is a clean, round fantasy. To get that travel time, people imagine a ship that cruises at a solid fraction of the speed of light. Not a timid 10,000 kilometers per hour, but perhaps 20 or 30% of light speed. They add a bit of relativistic time dilation as a bonus, so the crew feels an even shorter span than observers back home. Then they quietly compress everything else. They assume a propulsion system that can reach those speeds. They assume a structure that can survive decades of operation. They assume life support that never fails in a truly catastrophic way. They assume a mission clock that never slips. The problem is that every one of those assumptions hides an entire frontier of difficulty. Take propulsion, the most serious current interstellar concept that reaches into that high-speed regime is not a starship full of people. It is a plan to push tiny probes, no bigger than postage stamps, with a forest of ground-based lasers. The idea, often called breakthrough starshot, is to give a wafer-sized craft a blinding burst of acceleration, driving it to perhaps a fifth of light speed in minutes. After that, it coasts in the dark for roughly 20 years until it flashes past the Proxima system. On paper, that gram-scale mission already stretches our engineering. The laser array would need to be vast, drawing on power comparable to a major city. The atmosphere would distort and absorb the beam, so designers talk about high-altitude or space-based platforms. The sail material must be almost impossibly thin and reflective, yet strong enough not to tear apart under intense light pressure. The beam must stay locked on a target that races away, with exquisite control for the whole burn. And even if all of that works, the tiny probe cannot slow down at the far end. It will streak through the target system in a few brief, blinding moments, snap whatever measurements it can, and then vanish into the night forever. Now try to imagine scaling that from a gram to 100,000 kilograms for a bare-bones human ship. The sail area must grow. The beam power must jump by factors of many orders of magnitude. The structural demands explode. The waste heat from the laser impact becomes a serious threat. What looked just about plausible for a dust mote-sized robot becomes absurd when you swap in a habitat, shielding, food stores, water, and the human nervous system. The 40-year dream leans on a propulsion scheme that barely works for something you could hold in your hand. Even if we ignore lasers and imagine a different kind of advanced drive, the realities do not bend easily. A fusion rocket might promise exhaust velocities high enough to make interstellar cruise speeds less crazy. Antimatter drives sound even better. Yet to shorten the Proxima trip to a few decades with a sizable crew, you must accelerate to a high fraction of light speed, then, at some point, flip the ship and burn just as hard to slow down. That means your fuel needs go up, not just for departure, but for arrival. Every kilogram of destination braking propellant has to be carried and accelerated during the first half of the trip. The mass spirals we saw earlier return with a vengeance. A hull designed to survive micrometeoroid impacts at those speeds must be tough and layered, not thin and graceful. Radiation shielding for decades in deep space must be thick, not symbolic. Life support must be overbuilt. Redundancy must run through every system. Each of these pushes the dry mass higher. Every bit of added dry mass pushes fuel mass higher. Every extra bit of fuel mass demands a stronger structure and even more fuel. You can tweak the parameters, choose exotic propellants, and imagine nearly perfect engines. The wall does not really move. Then there is time. A 40-year mission does not only mean 40 years of travel, it means 40 years of continuous operation for power systems, computers, environmental controls, and all the quiet background machinery that makes the difference between a habitable cabin and a tomb. On Earth, we celebrate planes or satellites that last a few decades as remarkable. Most complex machines demand frequent maintenance, spare parts, and human hands. For a Proxima crewed ship, many subsystems would need to be built with a reliability level we have never achieved at scale, because failure does not mean expensive repairs. It means the end of the story. Communication becomes another pressure point. During the long cruise, light time to home grows to years. A message you send might arrive at Earth well after political regimes have changed and institutions have evolved or fallen. The mission could outlast the funding cycles, the enthusiasm, even the civilizations that launched it. Planning for repairs or resupply is impossible. You would be betting the entire trip on a culture that can maintain continuous attention and support over nearly half a century, and on a crew that can maintain a shared sense of purpose in a vacuum where every signal from home is old news. We can see how fragile that assumption is by looking at our real record. The Voyager missions have lasted for decades, but they are simple in comparison, with minimal moving parts and no human lives aboard. Ground teams have nursed them along with ingenious workarounds and software patches. Even then, instruments fail one by one, power fades, and signals weaken. The idea that a starship packed with complicated, interdependent systems could run hot for 40 years without a cascading failure seems more like wishful thinking than conservative engineering. The 40-year story also tends to gloss over what happens after arrival. Suppose, through some combination of luck and genius, you do get a crewed ship into the Proxima system. Now what? You are in orbit around a small, active red dwarf that flares often. The planet you came for might be tidally locked, with one hemisphere in eternal day and the other in eternal night. Its atmosphere, if it has one, may have been stripped or altered by stellar winds. It is not a second Earth waiting for the first human footprint. It is an alien world that will demand its own decades of scouting and adaptation before any hope of long-term settlement. If you intend the mission as a there and back again journey, with the same crew returning home, you are now talking about many more decades. A stay-in system, refueling or rebuilding, time to explore and learn, then another long acceleration and braking cycle to go back. Even if everything works, the trip stops resembling a human lifetime and starts to look more like an entire historical era. The children of the original planners might meet the returning crew as elderly strangers, or not at all. In practice, any serious crewed attempt on Proxima would probably be designed as a one-way or many-generation project from the start. The people on board would know they are leaving home forever. They would aim not to visit and come back, but to build a root system there that can outlive them. That shifts the mission from a 40-year jaunt to something much closer to an open-ended colonization effort. And with that shift, the line between interstellar travel and generation ship thinking blurs. The gap between the fantasy and the reality is why some critics call the 40-year frame a lie. Not because anyone is maliciously misleading, but because the simple number hides the scale of the obstacles in a way that distorts our intuition. Saying that Proxima is 4 light-years away and that a ship could get there in 40 years if it travelled at a certain fraction of light speed is technically true. It is like saying you could walk around the world in a reasonable time if you never slept, never stalled at borders, and never ran into an ocean. It would be easy at this point to throw up our hands and declare the mission impossible. To say that crewed journeys to Proxima are forever out of reach. That might be too strong. Physics does not absolutely forbid a civilization from gathering the necessary energy, building massive beam arrays, or constructing fusion or antimatter ships that run for decades. What the laws of nature do is set the bar staggeringly high, in a way that demands not just better engines, but an entire planetary economy and culture organised around a single epic project. And that is where another realisation creeps in. If we need to mobilise an entire world for centuries to send a few hundred people to the nearest star, maybe we should ask whether those resources could be used to push more reachable frontiers instead. There is a lot of room already inside one solar system to build habitats, cities, and industries. Asteroids can become mining sites, free-flying stations can host thousands, gas giant moons can be laboratories for chemistry and life. Once we admit that Proxima is not a near-term destination for ordinary human missions, we are forced to think differently about where our ambitions can actually take root. Yet even if crewed Proxima missions remain science fiction for a long time, the way we think about them shapes our ideas of what is possible across the galaxy. When scientists run numbers and realise how hard it is to reach even the nearest star with living passengers, they start to doubt stories in which alien civilizations casually hop between suns as swimmers cross a pond. If the distance to Proxima is a slog that bends economies and technologies to the breaking point, what does that imply for interstellar empires spanning thousands of light years? To explore that question honestly, we have to look beyond the dream of fast voyages with a single crew and face a much stranger picture. Maybe any civilization that truly commits to the stars will not travel like heroic sailors on a single continuous journey. Maybe it will travel as a slow, self-contained ecosystem, a worldlet, carrying not just a crew, but an entire miniature society, built to last for centuries inside a metal shell. When you follow that line of thinking, the story of interstellar travel stops being about speed at all and becomes something much more unsettling. Imagine a ship that is less a vehicle and more a world.
Inside, there are streets and gardens, homes and workshops, schools and hospitals. The walls curve up and over until they meet in an artificial sky, and if you walk far enough, you arrive back where you started without ever seeing a horizon. Outside, the hull is a silent shell moving through interstellar darkness. There is no destination within any single lifetime. This is not a voyage in the way we usually mean it. It is a decision to put a self-contained human ecosystem into motion and let generations live and die inside it while the stars drift slowly past. To make such a place livable, you have to replace one of the most taken-for-granted gifts of Earth, the gentle pull that keeps your feet on the ground. The usual idea is rotation. Take a cylinder or a ring, spin it, and let centrifugal effect push people toward the inner wall. Designs like the conceptual chrysalis habitat imagine structures many kilometers long, with towns arranged on the inside surface and an illusion of an arching sky above. Rivers might run along the curve. Trees might grow in arranged forests. The whole environment would be tuned so that, to a child born there, down feels normal, and the fact of spinning is invisible background. Behind that calm scene, however, every molecule is counted. A generation ship must be almost perfectly closed. Water cycles through pipes, soil and bioreactors with minimal loss. Carbon moves from air to plants to bodies and back again. Trace elements must be captured and reused. On Earth, we lean on huge reservoirs, oceans and rocks. We waste and the planet absorbs. In a closed habitat, there is no outside to absorb mistakes. Filters clog. Microbes evolve. Small imbalances can grow quietly until crops fail or air quality drifts. Over a voyage lasting centuries, the system must hold steady against entropy and against billions of small human decisions. The population itself is not a handful of heroic explorers. To keep genetic diversity healthy across many generations, you need thousands of people, not dozens. A crew of a few hundred might work for a single mission span, but over centuries, it would slide into inbreeding and vulnerability. So the starship interior must be a small city, with neighborhoods and social layers, not a cramped outpost. As soon as you accept that scale, questions of who is allowed to be born and when become inescapable. Space is finite. Resources are finite. If people have children whenever they wish, population will overshoot. If someone sets strict birth quotas, that person or institution holds extraordinary power over the most intimate parts of life. This is where the technical elegance of a rotating habitat collides with the messy reality of human society. A world ship must have rules about reproduction, work, and resource use that are tighter than anything most of us have ever experienced. Do you let elected councils decide who may have children and how many? Do you bake the policies into hard-coded systems that cannot be easily changed, even if later generations disagree? Do you risk loose freedom and trust that culture will self-regulate? Each option carries its own kind of danger, from creeping authoritarianism to chaotic growth and eventual collapse. The ethics do not stay abstract when you realize that tens of thousands of lives inside a sealed tube depend on those choices. Then there is the question of consent. The original volunteers, the first generation to board and launch, can sign forms and make vows. Everyone after them is simply born there. They have no memory of oceans or open skies. Their world has walls a few meters thick and a known radius. From the moment they are old enough to understand words, they are told that their purpose is to maintain the ship and nurture a future they will never see. Some will accept that with pride. Others will look at the stars beyond the hull and quietly wonder why they are paying the price for a decision made by people long dead back on a planet they have never touched. To keep such a society from unraveling, education becomes as critical as air recycling. Every child on a generation ship is not only a person, but also a future technician, doctor, farmer, and caretaker of ancient machinery. They must learn physics, biology, systems engineering, and the history of why the ship exists. They must understand which rituals are preferences and which are literally life support protocols disguised as culture. One lazy generation that treats maintenance as someone else's problem
could start a chain of failures. One charismatic leader who convinces people that the mission is a lie or a mistake could turn routine repair work into a point of rebellion. We can draw rough lessons from long-lived societies on Earth. Empires, city-states, and cultures have risen and fallen many times across history. Some lasted centuries, held together by shared myths, laws, and institutions. Yet none were completely stable. Corruption crept in, factions split, external shocks hit. The difference is that when a terrestrial society fell apart, there was physical room for survivors to move, regroup, and build again. In a generation ship, there is nowhere to run if politics go bad. The ruling class and the opposition are trapped in the same metal drum, and the life support system does not care who wins. Inequality would be another lurking fault line. If one ring or deck has better access to light, water, or structural safety, people will notice. Privilege tends to harden into class over time. On a planet, the poor might move or protest or be absorbed into a different region. On a ship, the separation is stark. Those in control might justify their status as necessary for the mission. Those excluded might start to see the mission itself as a story used to keep them compliant. In that environment, a single riot at the wrong place near a critical system is not just a political event, it is potentially an extinction event. All of this pushes designers toward more aggressive management of human behaviour. If the stakes are that high, some argue, perhaps it is kinder to shape psychology from the start. You could imagine education systems tuned not only to teach facts, but to gently sculpt personalities toward conformity and cooperation. You could imagine genetic selection that biases people away from impulsive violence and toward patience. You could imagine media and rituals that continually reinforce loyalty to the mission as a sacred duty. These measures might lower the risk of revolt. They also blur the line between guidance and deliberate, permanent manipulation of entire bloodlines. There is a darker edge beyond that. A society might decide that free choice is simply too risky for a centuries-long voyage in a fragile can. They might enforce strict surveillance, algorithmic monitoring of mood and speech, and immediate intervention at any sign of dissent. They might define mental health as alignment with mission goals and treat skepticism as a disorder. From the outside, we can see the horror in that idea. From the inside, leaders who grew up under these constraints might see them as normal and necessary, as vital as a pressure door or a fire break. Once entered, that kind of social architecture is hard to undo without unleashing tensions it was designed to suppress. There is also a quieter, more personal hazard. Life on a generation ship could become numb. Not dramatic, not violent, just drab. The view out of the windows would change incredibly slowly. The daily work of checking filters, tending crops, and repairing machines could start to feel like a treadmill that never stops. Without a tangible sense of progress, without vistas that change, many people might slip into quiet despair. Even if systems remain stable, the culture could hollow out, going through motions while the original sense of wonder fades. A world that was built with epic ambition might turn, from the inside, into a grey factory for maintaining descendants. For all of these reasons, some thinkers have argued that true generation ships are less likely than they first appear. The technical challenge of building a rotating city in space is enormous but imaginable. The challenge of designing a human culture that stays healthy, motivated, and reasonably free across 10 or 20 generations in a sealed can may be even harder. When you weigh those problems against the lure of other options, you start to see why people are tempted by more radical shortcuts that change the terms of the journey itself. Instead of carrying a full civilization awake and active across centuries, maybe we try to shrink the amount of lived time inside the voyage. That points toward two intertwined dreams. One is to build engines powerful enough to shorten the trip itself, using nuclear reactions rather than chemical ones. The other is to learn how to slow human bodies and minds almost to a stop, through hibernation, suspended animation, or something like it, so that long stretches of transit become a kind of controlled absence rather than a lived century. Whether those dreams bring the stars closer, or simply open a new set of risks, is its own deep question. Those dreams of changing the journey itself fall into two big families. One leans on new kinds of fire, tapping the power of the atomic nucleus to push starships faster than chemical fuel ever could. The other leans on changing our experience of time, slowing our bodies or minds so that long voyages feel short or vanish altogether from personal memory. On paper, they look like clean escapes from the trap we have been circling. In practice, they drag us into some of the most controversial places in physics, biology, and politics. The boldest nuclear idea is also one of the oldest. In the early Cold War, some engineers looked at the raw energy of nuclear blasts and did something shocking with it in their heads. They imagined a ship that rides a trail of small nuclear explosions. Instead of burning fuel inside a chamber, you drop compact bombs out the back. Each detonation slams into a huge metal plate at the stern, and a system of shock absorbers turns that brutal push into a more gentle shove for the crew. Repeat this hundreds or thousands of times, and the ship gradually climbs to speeds no chemical rocket could ever touch. In drawings and reports from that era, the vehicle is surprisingly simple. A stout disc or cone, a massive pusher plate, a stack of nuclear charges in the hold, and a crew habitat perched on top away from the worst radiation. The numbers are seductive. Nuclear pulse propulsion can in principle throw exhaust out the back at tens of thousands of kilometers per second. That means far better performance in the rocket equation. A ship driven this way could carry heavy armor, thick radiation shielding, and spacious habitats, and still reach the outer planets in reasonable times. Some calculations suggest interstellar precursor missions might be possible in centuries rather than millennia. Yet almost every part of that vision collides with real-world limits. To test the system properly, you would have to set off a large number of nuclear explosions, at first in the atmosphere and then just above it. The fallout would not care that it came from a peaceful spacecraft rather than a weapon. Global treaties banning nuclear tests grew out of exactly that kind of contamination. Even if you moved all launches to deep space, every pulse is still a charge built on weapons technology. Each ship becomes a flying stockpile that could be repurposed with only modest changes in intent. There is also a quieter, structural problem. A pusher plate that survives repeated nuclear hammer blows must be incredibly tough. Over time, it will erode, crack, or warp. The shock absorbers must cycle perfectly again and again. If any part of that mechanical chain fails badly, the next pulse might rattle the ship to pieces. You can add redundancy and margin, but the stresses are extreme. The same explosions that give you unrivaled thrust also constantly try to tear your engine apart. More modest nuclear hopes focus on reactors rather than bombs. In a nuclear thermal rocket, a compact reactor sits where a chemical combustion chamber would be. Instead of burning fuel and oxidizer, you run a light propellant like liquid hydrogen past the hot core. It heats, expands, and flies out the nozzle at far higher speeds than chemical exhaust. The thrust is still lower than a thunderous chemical launch engine, but the efficiency is much higher. That means for the same propellant mass, you can change your speed by a much larger amount. Decades ago, projects on paper and in desert test sites showed that nuclear thermal engines are not mere fantasy. They ran reactors, heated propellants, and measured performance that would cut travel times for Mars missions and deep space journeys. In a solar system where every kilogram is expensive, that kind of improvement reshapes mission planning. You can launch fewer heavy stages, carry more cargo, or simply shorten trips, which eases life support demands and crew stress. For interstellar travel, nuclear thermal is still far too weak on its own, but as a stepping stone, it changes the scale of what our species could realistically build close to home. A cousin approach uses nuclear power in a different way. Instead of heating propellant directly, you let the reactor generate electricity. That electricity runs ion engines that throw tiny amounts of reaction mass out the back at extremely high speed. Thrust is feeble, almost a whisper, but it can be sustained for months or years. Over long spans, these low-thrust, high-efficiency drives can build up impressive velocities. They are perfect for robotic cargo tugs, outer-planet probes, and slow but steady transfers where no one on board is counting days. So why are none of our current crewed ships nuclear-powered? Part of the answer is fear. Launching a live reactor on top of a rocket means accepting that, If the booster fails early, radioactive material could be scattered across land or sea. Even if designs try to keep cores cold and intact until they reach safe orbits, accidents have a way of ignoring paperwork. Another part of the answer is politics. Any technology that places lots of compact, high-power reactors in orbit or beyond will make militaries and watchdogs tense. The line between propulsion and potential weapon can be thin. Treaties, public opinion, and the legacy of nuclear accidents on Earth all combine into a kind of social drag. Engineers can calculate elegant trajectories and reactor designs. Lawmakers and citizens must decide whether they trust those designs enough to live under the launch path. The result is that our nuclear dreams have stalled in a strange place. On drawing boards and in simulations, they look like the key that could unlock fast movement around the solar system. In the actual sky, our crewed vehicles still burn chemical fuel and accept long, slow arcs. Even if we imagine a future where that political knot is cut and nuclear propulsion becomes common, interstellar distances hardly budge. Powerful reactors and ion drives might get a large ship to a significant fraction of light speed over many years of steady acceleration, but the total journey time to nearby stars would still be measured in centuries in the frame of the ship, unless we are willing to pour truly staggering amounts of power into the effort. That is where the second family of dreams comes in, the ones that try to bend subjective time instead of external speed. The most dramatic version is cryonics, the idea of preserving a person at very low temperature so that biological processes effectively stop. In principle, you could cool crew members down, keep them in that suspended state for the duration of a multi-century trip, and then revive them at the destination as if no time had passed. Today, however, our efforts in this direction fall far short of that promise. Freezing complex tissues tends to form ice crystals that shred cell membranes and delicate structures. Even with chemical agents that encourage glass-like states instead of sharp crystals, warming and revival without damage remains beyond our reach for whole brains and bodies. What we can do, in medicine, is much more modest. Surgeons sometimes cool patients during certain operations to slow metabolism and protect organs from temporary lack of blood or oxygen. Experimental work in animals suggests that short-term induced torpor, closer to a deep sleep than full suspension, might be possible for slightly longer spans. Bears, ground squirrels, and other hibernating animals point to a natural template. Their bodies know how to dial down energy use, heart rate, and temperature, and then ramp them back up in spring without apparent harm. Translating that kind of seasonal hibernation to humans is not a simple copy. Our bodies are not built with the same switches. Prolonged inactivity leads to muscle loss, bone thinning, and blood clots. Cooling and rewarming strain the cardiovascular system. The brain is especially sensitive to oxygen drops and temperature swings. Any deep sleep lasting months or years would need to protect not just organs but memories, personality, and the subtle wiring that makes each person who they are. The fear is not only that a patient fails to wake, but that they wake changed in ways we do not yet understand. Even if the biological part is solved, the engineering around mass hibernation is sobering. A ship carrying thousands of sleeping passengers must keep their pods at stable temperatures and pressures for decades, with pumps, sensors, and control systems that never fully turn off. Maintenance cannot be done by the sleepers. Some crew must remain awake, cycling through shifts across generations to keep the hibernation systems themselves alive. The burden does not vanish. It simply shifts from everyone to a smaller, more heavily loaded group. Then come the ethical and psychological questions. Is it acceptable to send people on journeys they will mostly not experience, effectively compressing centuries of travel into a night that erases lived time? How do you handle consent from later generations born on Earth who never knew that their grandparents signed away the family line to a deep sleep voyage? If someone in hibernation begins to fail, who decides whether to attempt risky intervention or to let them go? The image of serene passengers slumbering peacefully can quickly dissolve into a more unsettling picture of vulnerable bodies completely at the mercy of technicians and policies. There is a softer variant of the time-bending dream. Instead of full hibernation, perhaps we induce torpor in cycles. Crews might spend weeks or months in low-activity states between bursts of wakefulness, reducing food, water, and oxygen consumption, and shrinking the period of conscious boredom and stress. Over a long mission, that could ease psychological strain and cut resource needs without demanding perfect, centuries-long stasis. But even cyclical torpor would require careful choreography to ensure that enough people are awake at any given time to handle emergencies. When we place nuclear propulsion and hibernation side by side, an interesting pattern appears. Both try to trade one kind of difficulty for another. Nuclear engines trade propellant mass for political, environmental, and safety risks. Hibernation trades psychological and social strain for extreme medical and ethical complexity. Neither feels like a clean, magic solution. Both make the ship more intricate and the margin for error thinner. Some scientists and futurists push further still and suggest we may have to change ourselves more fundamentally. If radiation is a relentless hazard, maybe we augment human DNA with genes from creatures that shrug off high doses, such as certain microscopic animals or bacteria. If long voyages demand patience beyond normal human levels, maybe we deliberately tweak neurochemistry or brain development to favour calm focus over impulsive drive. If we want bodies that can endure low-temperature torpor or slow down cellular aging, perhaps we alter repair pathways and metabolic switches at the genetic level. These ideas stretch the idea of an astronaut. At some point, heavily engineered humans become a distinct branch, adapted not to live on planets, but to live inside machines in deep space. They might tolerate higher radiation, longer isolation, and stranger sleep cycles than we can. From a mission planning perspective, that is a feature. From a moral perspective, it raises questions that echo the generation ship dilemma in a new key. Who decides which traits are desirable? How do the modified view the unmodified, and vice versa? What rights do people have over their descendants' genomes? On Earth, even small steps in genetic editing trigger intense debate. Using those tools to craft an entire line of deep space travelers would amplify every fear people have about eugenics and unintended consequences. There is also the stark reality that any mistake in such a program might not show up until generations later, when a hidden vulnerability surfaces under the novel stresses of space. When your test lab is an interstellar mission, rolling back a bad choice is no longer an option. All of this brings us back to politics in a wider sense. Building nuclear drives, orbital shipyards, hibernation facilities, and genetic programs is not something a lone inventor or isolated company can do. It demands decades of sustained investment, international agreements, and stable institutions. Our track record as a species on long-term, globally coordinated projects is mixed. We can achieve miracles when we align, from eradicating diseases to building immense particle accelerators. We also struggle to maintain focus on even well-understood threats like climate change, let alone speculative starships. Imagine the council or parliament that has to approve the first true interstellar project. They would weigh benefits that may not arrive for centuries against costs and risks that land on the current generation. They would face voters who will never see Proxima themselves. Other priorities will always press in: education, health, disasters, conflicts. In that noisy arena, a starship can sound like an indulgence, a cathedral project for descendants who might not thank you. Without a deep cultural shift in how we value future lives, interstellar plans may never move off the page. So we end up in a strange place. The physics of nuclear propulsion is not mystical. The biology of torpor and genetic resilience is not beyond imagination. The real barrier seems to be the fragile, political, quarrelsome species trying to weave these tools into a coherent, stable civilization. We can sketch paths where nuclear engines, sleeping passengers, and adapted bodies drift between the stars. We cannot yet sketch a credible story of how our current world evolves into the kind of long-sighted, patient culture that would build and launch them. If all of this feels abstract, one way to ground it is to look at what we have actually done already, with the tools and attention span we do possess. There is one small machine that has quietly been testing our ability to survive in deep space for nearly half a century, carrying a fragile radio and a tiny store of power into the dark beyond the planets. To understand the real scale of the challenge and the tiny foothold we have so far, we only need to listen to that aging traveller and see how little of the interstellar sea it has actually crossed. When Voyager 1 left Earth in the late 1970s, it was not billed as a pathfinder for starships. It was a robot geologist and photographer, a boxy bus of electronics sent to tour the outer planets, while a rare lineup made the trip efficient. Its primary mission was supposed to last a few years. It would fly past Jupiter, then Saturn, take pictures, sample fields and particles, and then fade into the background of history. Instead, it kept going. Decade after decade, its tiny radio whispered back across growing distances while its nuclear power pack slowly dimmed. If you could stand next to Voyager 1 today, you would see a machine that looks almost modest. A white dish about the size of a small room, a spidery framework holding instruments, booms extended like frozen limbs. There is no sleek hull, no glowing engine. It drifts in darkness that is nearly absolute, with the sun reduced to a star. Yet in terms of pure distance from home, it is the most extreme expression of our reach. No human, no other machine, has gone farther. The numbers are both impressive and humbling. Voyager 1 is now more than 100 times farther from the Sun than Earth is. Light takes well over 20 hours to make the round trip between its antenna and our receivers. When engineers send a command, they wait almost a day to know whether the craft even heard them, and another day to see if it obeyed. That lag alone feels like interstellar space. The craft has crossed the region where the solar wind dominates and now swims in a thin soup of particles that belong more to the galaxy than to our star. But when you compare its distance to the gap between the Sun and Proxima Centauri, the story changes scale. Voyager 1 has covered only a few hundredths of 1% of that journey. If the space between the Sun and Proxima were a road from one side of a continent to the other, Voyager would still be trudging through the first few kilometers outside the city. It is beyond the planets, beyond the heliosphere, and yet it is still very much in the Sun's neighborhood. This ratio is easy to miss when we hear big numbers without context. Billions of kilometers sounds huge until you set it next to trillions upon trillions. The spacecraft's speed is fast by any human standard, tens of kilometers every second. Yet that speed buys only a slow crawl on interstellar maps. It is like seeing a single grain of sand fall off a beach and realizing that the shoreline is still effectively untouched. There is another lesson wrapped in Voyager's long trip. The craft has survived this far because it is simple in the right ways. Its instruments draw tiny amounts of power. Its trajectory needed only a few planned course corrections. Its software is minimal by modern standards. Ground teams have squeezed new science out of it through careful reprogramming and clever use of limited resources. But the overall system is not trying to balance an atmosphere, recycle water, or keep a nervous system functioning. It is a patient machine that asks little and lasts long. When we imagine starships full of people, we should remember that contrast. Everything about a human habitat in deep space is heavier, more fragile, and more demanding than a silent probe. Life support has to run without interruption. Food must be grown or stored and rotated. Medical emergencies must be handled with no outside hospital. Electronics must be shielded. Psychological needs must be met. Take all of those requirements and stretch them over the kind of distances Voyager hints at, and the gap between what we can already do and what we dream about becomes brutally clear. Yet even Voyager's modest crossing has changed how we see our place in the galaxy. For the first time, instruments outside the bubble of the Sun's influence are measuring the density of the local interstellar medium directly, tasting the stuff between the stars. Those readings show that even the emptiest space is not truly empty. A few atoms per litre drift there, along with magnetic fields and cosmic rays. On scales of millions of kilometers, it feels like vacuum. On scales of light years, that thin haze becomes the ocean we would need to sail. When you zoom out further still, you leave behind individual spacecraft and even single stars. Our Sun is one among hundreds of billions in the Milky Way. Its position is not at the center, but in a spiral arm, winding around the galactic core every few 100 million years. If you could look down on the galaxy from above, it would resemble a giant city at night, with dense glowing districts and dimmer suburbs. Our entire solar system is a single apartment in one of those suburbs. On those scales, Even the distance to Proxima shrinks into insignificance. Neighbouring stars are separated by a few light years. The galaxy itself spans something like 100,000 light years across. Light leaving one side of the disk takes 100,000 years to reach the other side. In that time, entire human civilizations could rise, flourish, and disappear many times over. The most ambitious interstellar plan we can sketch today would move us barely from one street corner to another in that vast city. Beyond the Milky Way, the picture expands again. Our galaxy is not alone. It is part of a loose gathering called the Local Group, a small cluster of roughly a few dozen galaxies bound together by gravity. The Andromeda Galaxy looms largest among them, a spiral as massive as, or larger than, the Milky Way, gliding slowly toward a future collision with us, billions of years from now. Dwarf galaxies orbit and swirl around these two giants like tiny islands or shipwrecks caught in their combined pull. Even the Local Group is only a small node in a much larger pattern. On million light-year scales, galaxies gather into filaments and walls separated by enormous voids where almost nothing shines. Surveys that chart these structures show a universe that looks almost like a frozen web, with bright knots where galaxy clusters sit and dark gaps where only sparse gas resides. Our entire cosmic neighbourhood, the region that includes all the galaxies we could ever realistically influence, is a tiny knot in that web. At first glance, this might seem like merely a question of scale. Everything is bigger than we intuitively imagine. But perhaps with enough time and enough technological growth, a determined species could slowly hop from system to system, then from galaxy to galaxy, spreading outward. Maybe the fact that the universe is so large simply means that expansion is a long project, not that it is impossible in principle. For a long time, that was an attractive idea. Then we discovered that the universe is not just expanding, its expansion is speeding up. The basic evidence comes from different directions that all converge on the same unsettling story. Distant galaxies are moving away from us and from each other, with more distant ones receding faster. That alone fits with a universe that has been expanding since a hot, dense beginning. But measurements of how supernovae brighten and fade, combined with maps of the cosmic microwave background and the distribution of galaxies, show that the rate of expansion is not slowing under gravity as you might expect. It is accelerating. To make sense of this, cosmologists have added a term to their equations that acts like a kind of energy built into space itself. As space stretches, this energy does not dilute the way ordinary matter does. Instead, it keeps doing the same job, pushing on the fabric and driving further expansion. The details are still murky enough that we use a placeholder name, dark energy, a label that mostly admits our ignorance. Whatever it is, its effects on long-term travel are profound. Accelerating expansion means that there is a horizon in a deep sense, not just the horizon you see when you stand on a hill and look around, but a horizon of what can ever be reached even in principle. Light from very distant galaxies emitted today will never reach us, no matter how long we wait, because the space between us and them is stretching too fast. From our point of view, those galaxies slide over a kind of cosmic event line and become causally disconnected. They are still out there, but their future actions can no longer influence ours. The same is true in reverse. Any signal we send outward has a maximum range. Beyond a certain distance, even light, the fastest thing in the universe, cannot outrun the accelerating expansion. Those regions will never receive our messages. No probe we launch, no ship we build, can ever arrive there, even if we could push it arbitrarily close to the speed of light. The expanding fabric itself beats us to the finish line, carrying destination and departure away from each other faster than any arrow can fly. In practice, this horizon is extremely far away compared to our current reach. It includes most of the galaxies we can see in deep surveys. For a while, that can sound like a comfort. The part of the universe that is slipping beyond contact is not the part we are thinking about visiting next century. It is the deep background, the distant past, the almost unimaginable far away. But as the eons roll on, more and more galaxies cross that line. The sphere of possible contact shrinks. On very long timescales, The only galaxies that remain mutually reachable are those that are gravitationally bound together already.
For us, that means something very specific. The local group, with the Milky Way, Andromeda, and their small companions, is effectively our entire long-term playground. Galaxies outside this small cluster will, given enough time, drift so far away and so fast that no future society of ours, however advanced, could go to them or see what they become. The vast cosmic web will fade out of reach, strand by strand, until only the local knot remains. The contrast with our intuition is startling. We like to imagine the future as an open frontier, with new territory always waiting just beyond the next horizon. The accelerating universe replaces that image with a different one. It looks more like an island world in a dark sea that is slowly carrying every other island away. If our descendants someday fill every habitable niche in the local group, they would still inhabit a tiny shard of the total universe that exists. This realization also loops back to questions like the Fermi paradox, the old puzzle that asks why we do not see obvious signs of other civilizations if the galaxy is old and rich with planets. The harsh truth that interstellar and intergalactic travel are so difficult, combined with the fact that cosmic expansion is already drawing curtains between regions, suggests that most civilizations, if they arise at all, may remain stranded in small pockets. The silence we hear when we point our radio telescopes at the sky might not be a sign that nobody is out there. It might be a sign that almost nobody can shout loud enough or long enough for us to hear. From another angle, the shrinking, reachable cosmos turns our existing probes and observatories into something much more poignant. Every mission that flies, every telescope that maps the sky, is capturing information from parts of the universe that will eventually slide away beyond contact. The data we gather now is not just curiosity fodder. It is a permanent record of neighbours we will lose. In the far future, astronomers might look back at archives from our era the way we look at ancient fossils, as traces of a richer environment that no longer exists. You could see all of this as a reason to despair, a kind of cosmic prison sentence that says we will never roam the full universe like characters in old space operas. But there is a different way to read it. If the set of places we can ever touch is finite and slowly folding inward, then the value of each reachable star, each habitable world, each chance to learn about the universe up close goes up. Scarcity turns exploration from a luxury into something closer to a duty. That thought changes the way we might frame our efforts. Instead of chasing a hazy dream of endless expansion, we can focus on understanding and cherishing the small patch of cosmos that physics gives us. The challenge is not to conquer the universe, but to make the most of a narrowing window in which we can still talk to it, travel within it, and learn from it. That window is vast compared to a human life, and yet constrained compared to eternity. Somewhere between those extremes is the timescale that really matters for us, the stretch of billions of years during which stars still burn brightly and galaxies still shine. In that era, the local group is both a constraint and an opportunity. It defines the stage on which our species, or whatever follows us, can act. To understand why that stage exists at all, and why it is shrinking, we have to step back from rockets, habitats, and ships and look directly at the strange energy that seems to be woven into space itself. Dark energy is one of those phrases that sounds like a complete explanation, but is really an admission of confusion. It was born when astronomers tried to make the numbers match the sky and discovered that ordinary matter and radiation could not account for the way the universe is expanding. They measured how distant supernovae brighten and fade, and saw that those exploding stars were dimmer than expected, as if they were farther away than a slowing expansion would predict. Instead of coastlines gently easing apart, the galaxies were racing away faster and faster. Something was pushing on the fabric of space, and nobody knew what. To keep the equations from breaking, cosmologists added a simple term to their models, a constant energy density that fills space uniformly. It does not clump into stars and planets. It does not dilute when the universe expands. As more space appears, more of this energy appears with it, always keeping the same density. The effect is subtle when the universe is small and matter is dense. Over time, as galaxies drift apart and average density falls, the constant background of dark energy takes over
and drives expansion to accelerate. We call it a constant, but that is really just our best fit for now.
It might be something more complicated, a field that evolves slowly, or a sign that our understanding of gravity breaks down on the largest scales. For now, the important fact is not the label, but the trend. The space between unbound galaxies is stretching at an increasing rate. On human timescales, that change is invisible. On cosmic timescales, it is profound. An accelerating universe has a strange consequence. There is a horizon beyond which events can never affect us, not even if we wait forever. You can imagine drawing a sphere around the Milky Way that grows with time. Inside that sphere are galaxies whose light, emitted today, will eventually reach us. Outside are galaxies that might be visible now because we see their ancient light, but whose present and future actions will never be known directly. Their new light will always be outrun by the expansion of space itself. This horizon is not a physical wall. It is more like a moving boundary in a map of cause and effect. For a while, as the universe ages, the sphere of possible contact grows. Then, as dark energy dominates, that growth slows and asymptotically approaches a finite size. Beyond that scale, the rest of the universe is forever cut off. No matter how powerful your telescope, you will never receive fresh information from those regions once they cross that line. The same reasoning applies to travel. If you launch a ship toward a distant galaxy that is receding faster than a certain speed due to expansion, there is no engine you can build that lets you catch up. You and the target are being carried apart by the stretching of space faster than you can close the distance. The crew can aim, accelerate, and burn through fuel until their engines are ash. They will still never arrive. Physics itself moves the finish line faster than they can run. Right now, from our vantage point, most of the galaxies we can see on the sky are still inside the range of possible contact in principle. But that fraction is shrinking. As billions of years pass, more and more of the cosmic web slides beyond the horizon. Eventually, only the galaxies that are already gravitationally bound to us remain mutually reachable. That means the local group. Everything else becomes not just practically inaccessible, but fundamentally out of reach. In that far future, a traveller who looks up at the night sky from some world in the merged remnant of the Milky Way and Andromeda will see a very different view. Instead of thousands of fuzzy smudges, there may be only a single bright island and a darkness beyond. The evidence that the wider universe ever existed will be fossilized in ancient star catalogues and background radiation that has stretched beyond easy detection. Without careful theoretical work and historical records, even the fact of cosmic expansion might fade from awareness. The endgame goes further. As galaxies exhaust their gas, star formation slows and eventually stops. New suns no longer light up. Existing stars age, burn through their fuel, and die. White dwarfs cool. Neutron stars and black holes dominate. Planets, asteroids, and debris swirl in increasingly cold, thin light. Over unimaginable timescales, even those remnants may decay. Black holes slowly leak energy through quantum processes. Protons themselves might not be stable forever, although that is still an open question. The picture that emerges is bleak but elegant. A universe that began hot, dense and bright gradually thins out into darkness and cold. Energy spreads out, temperature differences fade. Without gradients to drive complex structures, chemistry slows. The cosmic stage becomes quiet. There may still be rare flashes of activity, but the general direction is towards stillness. Whatever stories are written, whatever lives and minds arise, all of them unfold during a finite special window when stars burn and galaxies still glitter. We happen to live deep inside that window, far from the beginning and far from the end, in an epoch that is uniquely good for cosmology. The universe is old enough that large-scale structures have formed, but young enough that the wider web of galaxies is still visible. It is also an epoch when life around ordinary stars has had time to develop multiple times and in multiple places, if it is ever going to. That timing is more than a curiosity. It defines what is realistically on offer for any species that wonders whether it can touch the stars.
When we talk about cosmic prison, then, we are not saying that someone has maliciously locked the door. We are describing a set of physical facts that quietly define the walls of our possible movement. Gravity binds clusters. Dark energy pushes unbound galaxies away. Thermodynamics slowly erodes the sharpness of structures. No law forbids us from exploring within those constraints, yet they do mean that the dream of roaming the entire universe will always stay a dream. The prison is simply the shape of reality. You might wonder whether there is any way around those constraints that we have missed. Perhaps some new physics discovered centuries from now will show that we can cheat the expansion, or open tunnels through space-time and leap between distant regions more quickly than light. Science fiction is full of such ideas, from warp bubbles to wormholes. In some cases, the equations of relativity allow exotic configurations that look suggestive on paper. In almost all cases, they demand forms of matter or energy that we have never seen and that may not exist. Even if some loophole does exist, there is a deeper issue. Relying on unknown breakthroughs is not a plan, it is a wish. The story we can tell honestly must be built on what we understand now, plus reasonable extensions, not on magic that erases hard problems without cost. The physics we have already tested across many experiments and observations says that distances are vast, energy is finite, and the horizon of possible contact is limited. That is enough to draw important conclusions about our place in the cosmos, even if future discoveries change some details. One of those conclusions is strangely hopeful. If only a small patch of the universe is ever reachable, then we have a clearer target. We do not need to map infinity. We need to understand, explore, and care for a finite, though enormous, neighbourhood. The local group, with its handful of major galaxies and list of smaller companions, becomes not just a random cluster, but our cosmic watershed. It is where any future versions of us will live out their long history, if we reach that far. This also reframes the scale of our current achievements. Right now, we have placed a few footprints on the moon. We have sent robots to wander Mars and dive through the plumes of a distant moon. We have thrown small metal messengers into interstellar space, carrying golden records and fading power sources. Measured against the size of the local group, this is almost nothing. Measured against the total history of one species that only recently learned to use electricity, it is extraordinary. The contrast between what is possible in principle and what we are actually doing can feel like an accusation. If we could, with enough patience and care, spread knowledge and life across thousands of systems in our small cluster, why are we still struggling to keep one fragile planet stable? If we know that cosmic conditions make this epoch uniquely rich in accessible information, why do we sometimes treat research and exploration as luxuries to be cut when budgets tighten? You can hear, beneath these questions, a soft prompt asking us what kind of ancestors we want to be. From another angle, the limits of interstellar travel also challenge some of our old stories about destiny. We often talk about going to the stars as a way to escape our problems at home: climate change, conflict, resource depletion. The fantasy is that new worlds will offer clean slates. The reality is that our physics tells us the opposite. Nothing anywhere in the universe will ever be as easy to inhabit as the world that already shaped us. And the scale of effort required to move even small numbers of people to another star dwarfs the effort required to heal one planet. If we accept that, then interstellar travel stops being a convenient exit door and becomes something else. It becomes an act of curiosity and long-term stewardship. Sending probes to nearby stars is a way of honouring a brief window in which such journeys are even possible. Building habitats in our own system, and perhaps, someday, around other suns in our cluster, is a way of ensuring that life, thought, and culture continue, even as cosmic conditions slowly change. It is not a plan B for a failed Earth. It is a plan A for a species that chooses to grow up. None of this requires that every human dedicate their life to rockets and astrophysics. The work of building a civilization that can think in millions of years also includes humble tasks. Education that teaches not only facts, but a sense of shared future. Institutions that can survive changes in technology and politics without becoming brittle. Cultures that value depth of understanding over short bursts of distraction. These things sound distant from starships, yet without them, no starship plan will ever endure long enough to leave the pad. There is another layer of meaning here that is more personal. You and I will never see a human landing on a planet around another star. We will never walk in the combined halo of the merged Milky Way and Andromeda, or witness the last bright days before starlight fades. Our entire lives are tiny segments inside this much larger arc. That can make everything we have discussed feel remote, like a movie we watch rather than a story we inhabit. But remember that every distant milestone, if it is ever reached, will be reached by a chain of choices that includes very ordinary days. A scientist who refines a cosmological model, an engineer who improves a life support valve, a teacher who sparks a child's interest in the night sky, a leader who decides that cutting funding for basic research is a bad trade for a brief political gain. None of those moments will appear in a future headline that says, "Humanity is now a multi-star civilization." All of them are part of the unseen foundation under any such headline. Thinking on cosmic scales is not about waiting for grand events. It is about seeing how small actions ripple forward through time. So where does that leave us? Standing here on one planet under one star, in a universe that is far bigger than we can ever cross, and yet shrinking in terms of what we can ever touch. It leaves us with a choice about how we interpret our limits. We can decide that they make everything pointless, or we can decide that they give weight to every act of understanding and care within the small but real sphere of influence that physics grants us. The accelerating expansion of space and the harsh barriers to interstellar travel do not erase the wonder of the cosmos. They concentrate it. They tell us that the night sky is not an endless playground, but a finite, fragile inheritance. They whisper that most of the universe will always remain a story we glimpse only through distant light. And they invite us to make the most of the part that is truly ours, by learning it deeply, exploring it with humility, and maybe, just maybe, sending a few fragile sparks of life and mind a little farther into the dark before the cosmic lights dim.